Okay. So here's our textbook that we're gonna work with. And I believe in the last class, we successfully finished the unit related to rates of change. Yes, here it is. And I told you it's gonna be important for our following unit, which is polynomial functions. It's basically a chapter, it's not a unit, but we can write it as a unit, polynomial functions. You can say chapter 3 in your copybooks, it doesn't really matter. And basically up to today, you already faced polynomial functions and you even solved some of them, but you may not even notice it. For example, a parabola or quadratic function is a polynomial function too, but it's just one of the cases for polynomial functions. So what is a polynomial function is? Before moving on to discovering that more deeply, the main techniques that you have to be familiar with are simplification and factorization of equations. Okay? So here, before we're starting, I would like to ask one of you, for example, Hala, can you answer this question? Number 2, how would you factor example number A in this question? Safa, maybe? Or Muhammad, anybody?
Do you like what the final answer?
Oh, sorry, I cannot hear you. Yep.
Like the final answer, you would get like something x plus 7 times x minus 4.
Look, you're almost right. Basically, what's happening when we're factoring any expressions, that the result should have less terms than the initial function. And for example, with quadratic function, you should be familiar with perfect square formula, right? It's a plus b squared equals a squared plus 2ab plus b squared. Do you know this formula? Perfect square. I believe you're supposed to know it from your previous classes, right? So, yep, okay, great. So the thing is, this factoring expressions is that you have to see these tendencies in expressions. Where can you factor? This is very important for studying polynomial functions. So for this particular example, question A, I can see that it has a form of perfect square, isn't it? Look, first term squared, then second term is first term times the second term, minus 28. For example, one way of factoring it, which is, I would say, a simple way, is to take x and simply factor it out from these two terms. So as a result, we're going to get x times x plus 3 minus 28. This would be our easiest simplification. But if you look closely, just give me a second. I want to check something real quick. Yep. So, sorry. Yep. So, what are we supposed to have in order to tell that this bracket should give us a complete square? So first of all, we know that second term is the first times second term 2 times, right? 2ab we're supposed to have here. In this example, we have 3x. If we divide it by 2, we would get x squared plus 2 times 1.5 times x, right? And minus 28. This is what we have right now. So the second term in perfect square, or b in this case, should be 1.5, right? So basically on this position, we have to have plus 1.5 squared, right? So we're gonna say plus 1.5 squared minus 28 and minus 1.5 squared, because we just added this term into our formula, right? We just added 1.5 squared, and we subtract 1.5 squared in order to keep the equality. So what's happening next? Now, this expression here can be folded into a perfect square formula. So I'm going to get x plus 1.5 squared minus, now outside of the brackets, 28 minus 1.5 squared. And let me use my calculator. So 1.5 squared, 1.5 squared is 2.25. So x plus 1.5 squared minus 28 minus 2.25. Okay, so my answer is basically x plus 1.5 bracket squared minus 30.25 minus 30.25. And yeah, that's how I've factored basically this expression. Is there any questions on that? So what I did, I've seen that here I'm supposed to get a perfect square somehow. And using algebraic properties when adding and subtracting the same value from the equation does not change its equality. So what I did, I see I need one more term to be here in order for me to factor this expression successfully. So I just add this term artificially, but I also subtract this term at the end of the expression in order to keep the equality. Do you agree with me, guys? Any questions on how to factor quadratic functions? Same one for this one, but here you have to use a different square of a difference formula. A minus b squared equals a squared minus 2ab plus b squared. If you look here, this is exactly what we're getting here. 2x squared is basically we can factor out 2 here right away. So let's see what we're gonna get. We're gonna get 2 bracket opens x squared minus 9x plus 14. 9x, 14. So basically, or we can, yeah, keep it like that. So now we have minus 9x plus 14. If it's 9 here and 9 is 2 times 4.5. So a second term should be 4.5, and we have 14 here. 4 point, so what we need here is so basically 4.5 squared, 4.5 squared gives us 20.25. 20.25. So here, instead of 14, we need 20.25. In order to do that, 20.25. We need to add 6.25. Look at x squared minus 9x plus 20.25 minus 6.25. You see why? Because I added it in order to finish this square, and now I have to subtract it to keep the equality. It's 25. And now this expression in the brackets, I can fold it using the difference of a square of a difference rule, and I'm gonna get equals to 2 times x minus 4.5 squared minus 6.25, bracket closes, so double brackets here. So this is my factorization for example number B. Do you have any questions about this? Because it's a very important part.
Do you have to use the perfect square method?
So you have to use complete square when you can see it, basically. If it's not there, there is no need to use this approach. For example, in this case, I only see that this equation has a similar form to perfect square or square of a sum, difference of square of a difference. So that's why I use it. I mean, if you simply factor out x from here, it won't be final factorization because it's not, you're not simplifying this expression the most you can. If you simply take x out from here, or for example, 2x from this expression, it's going to be only partial factorization. In this particular case, there is no other thing that you can do in order to factor out this expressions completely. Only a perfect square I can see here.
I mean, how I factored number 2a was like by regular factoring and getting like the 3x to become a plus 7x and a minus 4x. And then you just like take the x out from the first side and take the 4 out from the second side, which would leave you with x plus 7 and times x minus 4. If I give you that answer, would that be like completely incorrect?
Okay, so can you repeat that one more time? I'll write it by you. So what you're doing is you take x squared plus 3x minus 28, and then?
You change the 3x to a plus 7x and a minus 4x.
Okay, x squared.
Which would leave you with 3x.
Yes.
Yeah, and then you just like take x squared and 7x together. And
Okay.
you remove the x out, so it would become x plus 7. And from the other side, it's you take the 4 out, so minus 4. It would become minus 4x plus 7, which means the brackets are the same. So what you do is you just take x plus 7 times x minus 4.
Yes, great. You're right. You see, I didn't see this solution here. But you're completely right, and this, I believe, is better than what I did.
Yeah, actually, I did the same thing for the B because
Yeah, here we can also split up 18x into two terms and use them separately for left and right hand side.
yeah, because in the end I got like 2 times x minus 2 times x minus 7.
Okay, so I believe you're right here. And think about difference over square or sum of a square, because okay, let's make the following rule. If you see in your function that you have, in fact, here, it wasn't really convenient to use square of a difference or sum of a square of a sum, because I have factor numbers here, 4.5, etc. They're not really nice. In other case scenario where you see, for example, let's say if it was in this example somewhere, yeah, x squared plus 3x minus 28, instead of being like 3x, let's say we would have 4x, and instead of 28 we would have like 3 or something. No, let's say we would have 5. It means that you only need to turn this 5 into 4, so 4 plus 1, in order to have a complete square on the left hand side. You see what I mean? If it is if you can split your terms in two and gain a perfect square formula, or like square of a sum or square of a difference, then do it. If no, this method that Hala showed you is really nice, but it wouldn't always work. These are, it looks like these examples are specifically made to solve them in the way that Hala presented. So what I'm saying, next time you see quadratic function, take a look if you can fold it into complete square, because that's one of the easiest ways of factorization, because like once you can do it in one step. But good job, Hala. Yeah, you're right. This is better than what I do. Okay, great. So tell me, do you know what it means when you're asked to write the equation of a function? Here you can see quadratic function. Are you familiar with that? How to identify, how should the formula look like? It's a tricky question because I'm not sure how you may did it before. Maybe you find some special points, etc. But what we have to learn in our today's class is how polynomial functions are being characterized. Sorry. How can the one polynomial expression differ from another one? Because there is such a thing as characteristics of polynomial functions. Okay, these characteristics help us to identify the shape, the curve of the exponential function, of polynomial function, and they also help us to identify critical points, direction of intervals of increase and decrease in polynomial functions. So these characteristics are crucial when solving problems, and you're gonna see why. So first we have to identify what polynomial functions are in total. In this table, on the left-hand side, you can see examples of polynomial expressions. On the right-hand side, you can see example of not polynomial expressions. You may ask what's different between them. That may be a good question, but We're gonna get to it slowly. So basically, polynomial functions occur when degree of the exponent in this function, for example, x squared, when degree of this exponent grows from 2 to 3 to 4, or another way, or more than 2. Whenever this degree is greater than 2, your function becomes part of the polynomial functions. As well, 2 is also a polynomial function. So quadratic function is a polynomial function as well. And there is a difference between polynomial functions and polynomial expressions. Why? Because polynomial expression has certain rules on how it must be written. Polynomial function is just a general classification of types of function. Here you can see on the left-hand side polynomial expression, and on the right-hand side not polynomial expression. First thing first, what we can see here, when we have a fraction exponent, x to the power 2.5, x to the power 2.5, if you see that in your function, it means it's not a polynomial expression. In polynomial expression, we try to keep all the powers whole numbers. Again, sine function is not a polynomial function, that's why it's not a polynomial expression. And there is no exponent here for x, as you can see. Also, 4x plus 5 is not a polynomial expression because it's exponential function. X here is as an exponent. So this is not a polynomial function. This is exponential. Okay. So next one. Here, this is actually a rational function, which are going to cover after learning polynomial functions. And also big chunk of all the material. And so on. So we looked through a few examples. Meanwhile, on the left-hand side, you can see that sometimes this position of terms is ordered in a specific way. And how is it ordered? The greatest exponent should come first. 3x squared should come first in the expression if it's the greatest exponent. I'm not really sure why here they put minus 4x in front, but basically, if you move minus 4x here, it would be a polynomial expression as well. Then you can see here, third, second, first, zeroth power. So exponents are positioned in the order of decrease. The greatest exponent comes first, second one is the next exponent, and so on. 3x plus 5, 3x minus 5, minus 7, minus 4x. These all are polynomial expressions, basically, which have this second or third term equals 0, right? If we have minus 7, it means we have only this part of this polynomial expression. It means all the rest of the terms, when x to the third power, x squared, x to the first power, they all have multiples of 0 in front of them. Basically, that's why we call minus 7 also a polynomial expression, because it's like part of polynomial expression, special case of polynomial expression where all the multiples equals to 0. Okay? And here is a definition that may help you to understand it. A polynomial expression is one variable is usually written with the power arranged from the highest to lowest degrees, as in this example of polynomial function. The phrase polynomial expression is often shortened to just polynomial. Okay? What makes an expression a polynomial expression, and what do functions that involve polynomial expression look like graphically and algebraically? So functions that involve polynomial expressions may take different shapes and forms. You're already familiar with quadratic function, which is simple parabola, as you can see on your screen. Meanwhile, functions of greater exponent, so let's say this is second degree polynomial. What if the polynomial is third degree? Well, then your graph gonna look something like this. You see, you have some similarities with parabola, but not too much. Now you have two highest points, right? Two minimums, one minimum, one maximum. With parabola, you had only one minimum or maximum. And also end behavior. Look at the ends of this function on both ends. If parabola was facing upwards on both ends, third degree polynomial function facing different ends. On the right hand side, it faces positive infinity in the y-axis. On left hand side, it aims towards negative infinity on y-axis. So from here on, I can make a conclusion, which we're going to see again later, that even degree polynomials, second degree, fourth degree, sixth degree, are going to have same end behavior on both ends. So if left-hand side goes to positive infinity, then the right-hand side also goes to positive infinity, the arms of the functions. For the odd degree function, odd, your end behavior is going to be opposite. If left-hand side is negative infinity, right-hand side is going to be positive infinity. If left-hand side is positive infinity, right-hand side is going to be negative infinity. Okay? This is one of the conclusions. Odd degree polynomials have opposite end behavior, and even degree polynomials have same end behavior for both ends of their function, whether it's going to be plus infinity or negative infinity. Second conclusion, you can see that the second degree polynomial, which is quadratic function, has only one minimum or maximum point. So if second power means one min max, right? Minimum maximum point. If you have third degree polynomial function, you can see that we have already 2 points like that. So it's going to be 2 minimums and maximums. You can write it down that the numbers of vertex for polynomial functions is 1 less than the power or the than the power of this polynomial function, than the degree of this polynomial function. Okay? Okay, good. We're gonna look into it once again. So I'm gonna clean the desk as if you're not against it. Let's look here. The simplest polynomial functions are functions that contain a single term. Use a graphing calculator to graph each of the following polynomial functions. Then copy and complete the table. So now we're gonna get familiar with general polynomial function notation. This is very important. Simplest polynomial functions are functions that contain single term. Remember, in the previous example, when we were investigating y is -7 as a polynomial function, I told you that it's only one term from a polynomial expression. So here, you have different scenarios when your only term is also your greatest exponent. For example, linear function, quadratic function, then cubic function with third power, quartic function with fourth power, and quintic with fifth. So what it basically means, if this is part of a polynomial expression with where only one term, how can we write down a polynomial expression in general form, right? How can we express any polynomial function by substituting it instead of some letters, right? Arbitrary values. So function f of x is a polynomial function that has form of an xn plus an minus 1 times xn minus 1 plus it would be an minus 2 xn minus 2, but we're going to skip that step and we're going to have the end of this sequence. End of the sequence is going to be a2 x squared plus a1 x plus a0. So what's important here? You can see that in this polynomial function form, greatest exponent comes first. You see it? N is the greatest number because then it comes n minus 1, 1 less, then it's 2, blah, blah, blah. N basically stands for degree of your polynomial function. Let's say if your degree of polynomial function is 5, you would have a5, so coefficient in front of x to the 5th power, plus coefficient in front of x to the 4th power, plus coefficient in front of 3rd times x to the 3rd power, plus a2 x squared, plus a1 x, plus a0. And you can see that exponent, oh, I'm sorry guys. We can see that exponent goes from greatest number, greatest power of exponent, to the least power of exponent, or exponent 0. A 0 does not have x in front of it because x has power of 0. And x to the power 0, you know, any number to the power 0 equals 1. That's why we don't write it. Okay? So we start with the greatest exponent, then we go like staircase one by one. This letter A stands for coefficient that stands in front of your exponent. And you can see that exponent is gradually decreasing all the way up to x to the power 0. So this is general note the formula, general form of polynomial function. Okay? And basically, this notation doesn't give us a lot, rather than understanding on how to identify polynomial functions. Later, we're gonna see some few more forms of notation of polynomial functions. It's gonna be a general form and coefficient form, because it's used in order to sketch the graph, but we're going to talk about it a bit later. For now, what I want you to do is to examine how each one of these simple polynomial function would look like. Remember, it's simplest polynomial function because it has only one term with the greatest exponent. First one is x, so it's a linear function, so it's going to be just a straight line. Second one is quadratic, which is parabola. They're going to be like this. Then it's cubic, that looks like this. But what is quartic? What is quintic? Can you figure it out? I already gave you 3 sketches of the graphs. You can use your notation tool in Zoom in order to sketch on this desk, if you prefer. Anybody would like to fill out this table for the class? Or you can do it even together. For example, domain and range, let Rana be responsible for it. how I can tell about existence of asymptote. Wherever, guys, I just want you to look into how each one of this function looks like. Go to a graphing calculator or wherever it is, try to find the form of quartic and quintic polynomial functions. And we're gonna make a short break from now for 10 minutes, and then we're gonna continue after that. Hello, everyone. Sorry for a little delay, but I hope you're well rested and we can effectively continue discovering polynomial functions. And guys, is everybody back? Everybody ready to go? Please. Thank you, Hala. Yep. Can the rest of you text something in a chat at least so I know that we're good to go? So I just want to give a little word to what we're studying here. Guys, in my studies, I've encountered real scenarios where you use everything that you covered in this course, in your past courses, even in calculus, in everything that you study at school. But talking about functions, you have to understand that this is the way that humanity learned to describe objective reality around us. And these rules that we are learning with you together right now, these are fundamentals of the world of math, okay? And using this language of mathematics, you will be able to understand incredible world that is around you. And these functions, you may look at this, these are just random graphs, and there are just few of them really have real world scenarios or representations, but it's not. When you start to study more complicated phenomena like electricity, magnetivity, or density, wherever, of a body, you see that even quintic functions can be faced there in that world. So every single aspect of mathematics is very important in understanding the real world around us and how scientists describing it. Polynomial functions have found their applications in many ways, starting from home appliances to rocket science. Because, for example, before we covered that a rate at which the flask fills out with the water also has an exponential or actually quadratic dependence sometimes. For example, rocket science, the formula for rockets is quadratic function, basically. And it's really interesting to see how this finds its place in the real world. And talking about polynomial functions, I see, guys, you did a great job sketching how other functions look like, but quartic, I'm not quite sure that it looks like this, because if it's quartic function, there is a few scenarios how it may look like. It can have up to 3 vertices, right? And as soon as it's quartic, end behavior should be same on both ends. So both ends of this function would look downwards, like this. No, wait. Like this. Yes, like this. We have 3 critical points, 1 minimum and 2 maximums in this scenario. If it would be facing upwards, it would look like this. So it would have 1 maximum and 2 minimum values, as well as end behavior would be facing to the positive infinity on both ends. Because remember, even degree polynomial functions, they have same end behavior. Odd degree, you can see somebody sketch the cubic and it's right. It's gonna, yeah, it was me. It's gonna be like this. Left side is on negative infinity, right hand side on positive infinity. While quintic, also an odd degree function, looks, yeah, this is pretty much right representation. We're gonna have 4 critical points, 2 maximums and 2 minimums, and it could be either like this or like this, the other way around. Also, and behavior is opposite. Positive infinity here, negative infinity here. Good, good. And domain and range. When we're talking about domain and range, linear function really spans from negative infinity to positive infinity in both x and y axis. But talking about, for example, quadratic function, simplest quadratic function would always look the following way. So it's easy that you know how the basic function look like. So when you add this, the following terms, next term, third term, you basically only changing the shape of this graph a little bit, but the main shape is given by the greatest exponent. Okay, even if you have x to the 5th power plus x to the 4th power plus x to the 3rd power, this function would look like quintic polynomial function. We mainly judge the polynomial function by the exponent, by the greatest exponent it has. So if you know how this basic function look like, you know all of them. So quadratic would be standard parabola facing upwards if the leading coefficient, this is important stuff, we didn't get to this yet, but I'm slowly giving you this information bit by bit. If the leading coefficient, and this is this guy in front of the greatest exponent, an, if this guy has minus, if this number is negative, it means our parabola would be flipped over the x-axis. So it's going to be facing downwards in case of a parabola. So basically what's happening, we're mirroring our function over the x-axis. That's what negative leading coefficient gives us. So for example, if we had minus x squared, it would be parabola facing downwards. And for parabola, realistically speaking, if it's x squared, it's facing upwards, and its minimum value is at point 0, 0, x0, y0. So its domain is still negative infinity to positive infinity, right? Because domain, we can take any x value, but the range is going to be limited. A range is going to be from 0 to positive infinity. Range is y from 0 to positive infinity. I don't remember exact notation for range and domain. You can check it out in the previous chapters. So talking about cubic function, it would have domain and range similar to linear function. It won't be restricted in any way, while quartic function will again have restrictions on its range, basically, right? Because we have maximum and we have minimum points. Remember, for odd degree function, we have local minimum and maximum, right? For even degree function, we also have local minimum and maximum, but some of them are absolute extrema. There is such a word, which means that the smallest number of the function. Okay, is there any questions on this? And by the way, where else? Existence of asymptotes. That's important chapter, and we're gonna look into it as well. Asymptotes in polynomial functions. For all of the standard simplest functions, there is no asymptotes, right? Asymptotes appearing. So we can have a horizontal or vertical asymptote. I'm not sure if you covered that at grade 11. Okay, but we're gonna look into it. One more thing. The greater the exponent is, the greater the power of the function is, the greater will be difference between value. It's explained in such way that exponent basically defines how fast our function is changing. Because, for an instance, x linear function has rate of change 0, right? The average, for example, it can have, it has constant rate of change because it can be increasing constantly, or it can be just going horizontally, or it can decrease constantly, wherever. But for quadratic function, the greater the x number is, the faster the rate of change, basically, right? Not all the time, because even for quadratic function, we know that on the beginning of the parabola, rate of change is pretty, it's huge, it's almost vertical, right? When x is a big number. And then it's slowly decreasing. First function is decreasing and the rate of change is decreasing. And then the rate of change is starting growing again. Is that right? So over exponential function or polynomial function, rate of change is not constant. When we look into any polynomial function, rate of change will change over the span of the function. So here, this is an interesting question. Why are the equations of the form y equals mx plus b and y equals ax squared plus bx plus c examples of polynomial functions? I can answer that question, but I hope you already can see it at this moment, because these are just two special cases of the same stuff. These are two cases of a general form for a polynomial function an x to the power n plus an minus 1, x to the power n minus 1 plus, and then we skip, plus a2x squared plus a1x plus a0. This is a general form, and these are just special cases when some of the leading coefficient of the coefficients in our formula are 0. For example, where an is 0, n minus 1 an minus 1 is 0, and so on, all the way up to, for example, here, we can see that the greatest exponent is 1, right? Greatest power of x is 1. So means everything until here just equals to 0. And here's the last two terms, a1x plus a0. Isn't it exactly the same stuff? And as well as talking about this one, difference is that only the second term, or a2x squared, does not equals 0. Is this clear, guys? Also, order is very important. If order is messed up, for example, you have x plus x squared plus x to the third power, right? Not from the greatest to the lowest one. Then it's not a polynomial expression, but it's still a polynomial function. Proper polynomial expression is written in the following order. The summary, and we'll even have some time to look into characteristics of polynomial functions. Make sure to note down this summary because it's useful to have it at your hand every time. So key ideas. A polynomial is one variable, is an expression of the form an times xn plus an minus 1 times xn minus 1, and so on, where a0, a1, all the way to an are real numbers, and n is a whole number. This is pretty obvious because n is an exponent and it's whole number, and it's like basically ordered pairs. And the expression contains only one variable with the powers arranged in the descending order. For example, 2x plus 5, 3x squared plus 2x minus 1, etc. I hope you got this idea pretty well. What do you need to know? In any polynomial expression, the exponents on the variable must be whole numbers. That's why at the very first table, there was a second part of non-polynomial expressions where x was raised to the power 4.5 and it was not a polynomial expression. A polynomial function is any function that contains a polynomial expression in one variable. One more time, a polynomial function is any function that contains a polynomial expression in one variable. The degree of a function is the highest exponent in the expression. For example, f of x equals 6x to the third power minus 3x to the second power and so on has degree of 3 because the greatest exponent is x to the power of 3. The nth finite differences of a polynomial function of degree n are constant. The domain of a polynomial function is the set of real numbers. Yeah, that's pretty right. For any polynomial function, we can take any x value. X is in the interval from negative infinity to positive infinity. Basically our domain. The range of a polynomial function may be all real numbers, or it may have a lower bound or an upper bound, but not both, right? If it's even degree function, we have lower bound as here or here, but we also can have an upper bound for even degree function. You see, maybe all real numbers as if it's an odd degree function, right? In odd degree function, we have all real numbers in the range. Or it may have a lower bound and upper bound as for even degree function. The graph of polynomial function do not have horizontal or vertical asymptotes, as we said, right? We're gonna see that rational functions have asymptotes in them. But in order to move on to rational functions, we need to figure out polynomial functions first. The graphs of polynomial functions of degree 0 are horizontal lines. The shape of the graphs depends on the degree of the function. 5 typical shapes are shown for various degrees. And it would be nice if you can memorize shape of each one of these standard functions up to 5th power. It's not so hard. So first property that you have to remember, that the number of vertices of polynomial function is one less than its degree. You see, we have 2, 1, 0, 3, 4. And simply by remembering this property, you can figure out how to sketch any of this function. So for example, 5th power, you know, okay, if I'm sketching the 5th degree polynomial function, I have to turn around once, turn around twice, 3 times, 4 times, and that's it. This is general shape of 5th degree function. I know that I have to turn around 4 times. Cubic, okay, I have to turn around 2 times. Change my direction. Change the interval where I'm increasing or decreasing, right? Because function is increasing, then decreasing here, then increasing again. That's why this minimum and maximum values are really important. Basically, later on, we're going to use them in our solution methods by slicing the function into intervals between this minimum and maximum points. And each of this interval would have special property. For example, here, the rate of change would be positive, negative, then positive, then negative, then positive again. You see, you can do a lot of stuff by only knowing this property of about number of vertices. Again, when you see a bunch of images and you're asked represent polynomial functions, determine which graph represents polynomial function, because maybe you're going to have something similar in your test. So basically what you're looking into is that polynomial functions, they have either infinite range, either limited from one side with upper and or lower boundary. And also, they would have x all rational numbers. So x value should be all included in this function. For example, here in the image C, you can see that end behavior is pretty odd. We know that polynomial functions have end behavior ending at infinity. Always gonna be infinity on one of the ends. And if you see something like this, no, it's a pass. It's not a polynomial function. because the end behavior is supposed to represent the infinite value, either positive or negative, and both ends should be facing same direction or opposite direction, if it's an even degree or odd. Okay? We're gonna skip this not so interesting problems for now. You can do this as part of your home assignment. It's very simple problems. But I really would like to talk about characteristics of polynomial functions. I already talked about it in the first part of our class, about the leading coefficient that is supposed to be negative, about remember, if the leading coefficient is negative, function is facing downwards. If it's positive, standard function facing upwards. This is one of the characteristics of polynomial function, but only one of them. So let's read this investigation real quick. Carl knows that he can describe the graph of a linear function from its equation. Using the slope and the y-intercept, he can also describe the graph of a quadratic function from its equation, using the vertex, y-intercept, and the direction of opening, right? So we can use the vertex, y-intercept, and the direction of opening in order to sketch the graph properly, in most accurate way, right? Y-intercept are pretty easy. It's just when we say x equals 0. When x equals 0, it means the graph is touching the y-axis. And the direction of opening, we can know it through the properties of polynomial functions that we covered before. Degree of the function, etc. Now he is wondering whether he can describe the graph of polynomial function of higher degree using characteristics that can be predicted from their equations. So he wants to use algebraic approach and give a general structure of analysis of polynomial function, no matter what degree it has. So here we have bunch of graphs, and you can see that all of them are polynomial function. But all of them have different number of terms in them. For example, here, in picture number C and B, both represent polynomial function of fourth degree, right? They all represent the fourth degree polynomial function. But even though they're same degree, they have completely different shape. And for example, here we can see that it faces downwards on the picture B. And we also can see that the leading coefficient in front of the greatest exponent is negative. On the other hand, this function is facing upwards, and its leading coefficient is positive. So conclusion, leading coefficient important? That's right. But what else can we get from these equations? As for me, they have too many terms in them to be able to analyze them in a perfect way. And we're gonna see how else can we write down the polynomial function in order to analyze this written notation with the highest accuracy, with algebraic accuracy. Here you can see they start to write down characteristics of each one of this function. And as an example, number A has a second degree, it's even, leading coefficient highlighted is +1. So the end behavior, positive infinity. If its leading coefficient would be -1, the end behavior would be negative infinity on both ends, right? Because it's even degree, both are same, and whether they plus or minus is identified by the leading coefficient. What is the leading coefficient as it described in this book? The coefficient of the term with the highest degree in the polynomial. Okay? Coefficient of the term with the highest degree in the polynomial. 2x to the third power is the greatest degree in the polynomial, so minus 2 it is. The leading coefficient is minus 2. Minus 2 is negative number, so the end behavior would be respective to the negative leading coefficient. If it would be positive, it would be like this. It would be negative infinity on the left-hand side and positive infinity on the right-hand side. But since it's minus, it's other way around. Okay, this is about leading coefficient. What this leading coefficient gives us. For even degree, simply switches the sign of end behavior on both ends. Take a notice that x is the same, x negative infinity and x plus infinity. Basically what happens when we go all the way to the left and what happens when we go all the way to the right. Number of turning points is 1 because number of turning points equals to the degree of a function minus 1. Remember that, this is very important. This is also one of the characteristics of polynomial function. Here it is, question D. What do you think the maximum number of turning points that a polynomial function of degree n can have? N minus 1. If you can figure out any other polynomial function, let's say you want me to write a polynomial function of second degree. Okay, I would say y equals x squared minus 4x plus 1000. Still, this function shares property based on the leading coefficient that is positive, so it's going to be faced upwards. And also numbers of vertices is already predefined by the greatest degree, the exponent in the polynomial expression. Even function has a symmetry in y-axis, okay? Odd function, rotational symmetry around the origin. And neither even nor odd functions neither of the symmetries. So basically, you're gonna see the symmetry only in standard form. In any other shape, you can see that the graph can be stretched, compressed, and the graph is fluctuating. So this initial symmetry is getting lost. Once your function turns from simplest one into some general form. Absolute maximum and absolute minimum, another important characteristics. The greatest or least value attained by a function for all values in its domain. Remember what I told you? It could be a local minimum or local maximum. For example, here, this value on picture number B, this point is local minimum, right? It's local minimum. It's not absolute minimum, because there is places where this function even lower. But these 2 points on top, this one and this one, are absolute maximums, because if they're on the same line, because they're the highest this function will ever get. Absolute value, another characteristic. Absolute maximum, absolute minimum. All polynomial functions of even degree have an absolute maximum or absolute minimum. Yes, even degree always have at least one absolute minimum or absolute maximum, because and behavior, remember, and behavior is on the same side. It means that the function reached its minimum or maximum value and then bounced off it and went the other way around. Okay? Why must all polynomial functions of odd degree have at least one zero? They're supposed to have at least one zero. So when y equals 0, because if their end behavior is opposite, on their opposite sides, right? One facing down, one's facing up. They're going to cross the coordinate axis at least once. You see, there is no way to connect them without crossing the coordinate axis. Do you agree with me? At least once. It means if you have degree 5, you can have as much as up to if it's 5th degree, 1, 2, 3, 4. You can have up to 1, 2, 3, 4, 5 zeros. One more property. The maximum amount of zeros that the function can have equals to the degree of this function. Because basically it means the number of times that you can cross the x-axis. Of course, it can happen in another way around, where instead of crossing it back and forth, you're simply gonna jump over it once and start fluctuating here, right? This is also a possible scenario. So we can have minimum of 1 and maximum of n, which equals to the degree of polynomial function. Can the graph of polynomial function have no zeros? Yes, even degree function can have no zeros, because, for example, coordinate axis, our even degree function with similar end behavior on both ends can be just positioned in this way, in first, in second quadrant. So there won't be any zeros for this polynomial expression. Same way if it was mirrored over the x-axis or had a negative leading coefficient. Okay, let's look into this example to strengthen what we have learned up to now, okay? Because I think it's a lot of material to cover in one class, because these characteristics will become intuitive to you with time. But now you just have to try and make yourself to remember this. And I hope this example will help you. Describe the end behaviors of each function. The possible number of turning points and the possible number of zeros. Use these characteristics to sketch possible graphs of the function. So let's take a look into example number 8. First things first, that I noticed that it's written in a decreasing sequence, right, of the exponent, and my greatest exponent is 5. And what is 5? 5 is odd. The degree is odd, so the function has opposite end behaviors. One side negative, one side positive, infinity. The leading coefficient is negative, so the graph must extend from the second quadrant to the fourth quadrant, right? Because the leading coefficient is negative. So if it wasn't, it would be from left bottom to the right top corner, right? In this way, if it wasn't a negative leading coefficient. But since it's negative, so the graph must extend from the second quadrant to the fourth quadrant. Second quadrant, fourth quadrant. So what is the end behavior? As x travels to negative infinity, y travels to positive infinity, and as x travels to positive infinity, y travels to negative infinity. Okay? First, right away, simply based on two characteristics, the greatest exponent and the leading coefficient. Boom. You know already 50% about this function. So if x is a very large, let me explain you why it happens in this way. If x is a very large negative number, such as -1000, -3x to the power 5 will have a large positive value and will have a greater effect on the value of the function than the other terms. Therefore, the graph will pass through the second quadrant for very large positive values of x, right? For very large positive values of x, -3x to the power 5 will have a large negative value. Therefore, the graph will extend into the fourth quadrant. Make sense? Makes sense. Because if we raise negative number to the fifth power, it will give us negative number. If we raise positive number to the fifth power, it will give us positive number. Here minus in front, so it should be negative. This minus in front must be positive. Using the end behaviors of the function, sketch possible graphs of a fifth degree polynomial. To pass through the second quadrant and extend into the fourth quadrant, the graph must have an even number of turning points. Is that correct? It should either have no turning points, or it should have an even number of turning points. Realistically, usually polynomial functions cannot have 0 turning points. I mean, they could if it's a third degree, right? Third degree can have 0 turning points. Okay, wherever. So sorry for that. We're gonna look into it in the next class, but for now, using the end behavior, we already are able. Sorry. Using the end behavior, we're already able to sketch graph in a pretty accurate way. In order to be more accurate, we can also say that f of x may have 0 2 or 4 turning points. Right, 0, it could be 0. We can have up to 4 turning points if the degree is 5, right? We can have from 0 to 4 turning points if degree is 5. And here is 0, here is 1, here is 2, here is 1, 2, 3, 4. Again, 1, 2, 3, 4, but in another way. So our function can fluctuate in this range, but the end behavior would be solid as we defined it. Okay, as well as for the second example where we have a fourth degree. Same way, you look into the end behavior in both ends based on the leading coefficient. You figure out that it's supposed to be positive on both ends. And now you just have to play with number of turning points. And turning points, remember, number of turning points maximum is n minus 1. That's it. N minus 1, leading coefficient, and even or odd degree of the function. That's what you have to remember to the next class. Please be confident with these characteristics of polynomial function. And thank you for the class. We're going to finish at this moment and we're going to take off from the same page. Is there any questions about characteristics of polynomial functions before you leave? Thank you, Safa. You have a great day too. Thank you for working today in class with me. You too, Mohammed. Thank you. Bye-bye, Hala. Thank you so much. Have a nice day too. Okay, if no questions, have a good day, everyone. Bye-bye.